This video is for Friday, the 16th of February. This is Hydrologic Engineering class number 17. Homework number 5 is due on Monday before class, and that's the one where you're going to be applying the unit hydrographs and the S hydrograph method. So please feel free to reach out if you have any questions on that assignment. What we're going to be doing today is moving on to the next step in the process of being able to predict stream response in the face of rainfall events. And so we're going to be applying one of the most widely used rainfall models, the NRCS method.
I think this is an appropriate time for us to take a step back and think about what's the big picture of the course. Like what sorts of things we're trying to predict, what kind of input data is available. Because the NRCS method is one of the first specific empirical approaches that will accomplish on the watershed scale an estimate between the rainfall and the runoff. So I think maybe I've introduced this slide before, and if I were going to distill down into just a single sentence what we're trying to answer, like the big question of this course, it is, what are the runoff characteristics? And so not just the peak flow rate, but also the variation in time, like the temporal distribution of the runoff hydrograph. How long will it take to achieve the peak after a storm occurs? How long until the watershed drains down back to the base flow? So overall, what are the runoff characteristics for our area of interest? And of course, an area of interest is generally defined by where you're putting in either a road or a building. It's just some place that you're interacting with the stream location. So the input data that we have to account for is the rainfall. And we've talked about how there can be both variability in the timing of rainfall and also spatial variability. So in the previous lectures, we talked about, just as an example, how a hydrograph could be different if a storm was coming from the north and headed southward versus if a storm was headed from the south of a watershed northward. And how if the direction of the drainage is matched by the direction of the storm, that you could have more of the flow arrive at the same time, even if the storm depth is the same. And we've talked about how antecedent moisture condition could radically adjust the runoff quantities, where if you have a 1-inch storm in a watershed during a dry period, that you may not see any response at all in the streams. But a 1-inch storm after several successive days of wetting is going to have a radically different runoff. So rainfall is obviously one of the important inputs to figuring out what the runoff is going to be like. And the abstractions, we've talked about different models and approaches to estimate evaporation. So the combined method, which takes into account both energy effects and aerodynamic effects. We talked about how the effect of vegetation can be accounted for, and interception with buildings, how that would reduce the amount of precipitation that ultimately turns into rainfall excess, and things like surface wetting and the depth of a storm that maybe is going to be bound to a surface and how that varies by slope. So all of these different factors, we've talked about some kind of either an underlying fundamental principle that tells us relatively more, relatively less runoff, depending on slope, depending on the density of the drainage within the watershed. We've talked about a lot of these factors to try and estimate their effects. Now, infiltration, of course, the two methods we talked about was green-amped and then the Horton method. And these are ways to estimate the declining potential rate of infiltration and how the suction head decreases as the pores begin to fill during an infiltration event. So the modeling that we're going to focus on in the coming weeks is turning some rainfall distribution into a runoff distribution and trying to predict what the shape of the hydrograph looks like. And it's not just the sizing of things like culverts and channels and bridges, that's affected by the shape of the hydrograph, but it's also larger structures like dams. We have to understand how quickly the water is going to be coming in, because dams, of course, are in part designed to release a certain quantity of water, and most dams will have a primary route that the water is going out. Maybe if it's an electricity generating dam, it will be through a penstock that is routed through turbines, but then there may be an emergency overflow and then a separate, not an overflow spillway, but sometimes discharge structures that don't necessarily have power attached, but it saves you from the surface scour that would occur if you're using the overflow spillways. A bit later, once we get into these computerized models, we'll look at how the hydrograph shape is affected by different techniques that we use to estimate time of concentration. So you remember that we talked about how there's kinematic wave, there's the Kirby method, the FAA approach. There's all these different formulas that have their own little niche applicability for predicting how long it's going to take between when the rain begins to fall and when it arrives at a certain location. So the time of concentration, not just for surface flow, but also as the water is going through the streams that may form. So the delay of the hydrograph as it travels through the watershed is part of what we'll calculate in those computerized models. And then towards the end of the semester, we're going to look at some risk assessment issues. And when you prevent a certain amount of flooding, how much economic value there is in preventing that flooding. So for instance, if you know how much damage is going to occur from a 5-year storm, and when there's a 10-year storm, how much more the damage is going to be, and the 25-year storm, what they normally do is develop inundation maps and knowing how deep will the water be and how deeply submerged would certain structures be at each return period. And so that if you're providing enough protection to prevent the 25-year storm from causing any damage, then you're capturing all of the value of the damage that would have occurred. So we'll look at balancing the cost of implementing flood control measures with the value of the damage that's avoided. So keep in mind this big picture overview, because we'll get kind of narrowly focused on nitty-gritty details of these sometimes silly empirical models that, is just curve fitting and a best attempt to try and mimic what's really happening with maybe some small tie into physical factors, but sometimes it's easy to lose track of the big picture. So just to represent it visually, we're going to start with rainfall data. We're going to turn that into runoff data. That's the job of a hydrologist. And so the NRCS approach, the NRCS stands for National Resource Conservation Service. And it's a subdivision of the United States Department of Agriculture. And it's kind of interesting. You wouldn't think that the USDA, the Department of Agriculture, would have much to say about hydrology, but actually they have quite a long history in the area of hydrology because it affects things like soil productivity and farming. And so there's a lot of really important climate and hydrology work that's done by the USDA. So this is one of their contributions to hydrology, is the NRCS model. And what they do is they take a rainfall hydrograph and they generate a runoff hydrograph from that by taking into account these physical factors that are known to have an impact. So things like soil properties, and thinking about how a well-drained soil, like sand, which has a really high hydraulic conductivity, would lead to a different runoff hydrograph than a poorly drained soil, like clay. It has a really low hydraulic conductivity. Things like land cover and the disruption to a watershed that occurs when previously native habitat is replaced with pavement and roof area. So the NRCS model is going to try and account for different soil, different land cover. And I'll show you a table today that illustrates how they try to account for it. There's a little bit of attention applied to abstractions, although the depth of sophistication in soil properties and land cover is much higher than what they're attempting to do with abstractions. But things like slope are accounted for, some of the stream characteristics and the shape of the watershed. All of these things can be accounted for in the NRCS approach. So the method here is, first of all, to look at what is the soil type and what's the land use characteristics in a watershed. And then there's just a simple empirical equation that says how much of the rainfall is going to get tied up in initial abstraction, how much of it is going to be retained in the watershed, and then therefore the leftover amount that's the runoff. And so it looks at depth. It looks at rainfall depth with units of length, and then it breaks up how much of that rainfall depth is going to these different locations: storage, infiltration, and then the leftover amount is rainfall excess. And then it uses a unit hydrograph to translate the depth with units of length into flow rate, which is volume per time. So, you may have a storm event in inches, and the NRCS method itself isn't going to say what this hydrograph shape should look like. It's just going to say how many inches of precipitation excess there is. And then you take that precipitation excess that's predicted and run it through the unit hydrograph, which we talked about in 2 previous classes, to get the flow rate. All right, so this is an important figure, and sometimes the conceptual questions I give in an exam is I would show you a graph or a picture and I'd ask you to explain it. So this is one that I think in previous semesters I've just maybe even blurred out what some of these labels are, and I asked students to identify each of these and explain the overall idea behind this. And so let me do that for you now. This is a rainfall hydrograph, which we've seen before. So on the vertical axis would be precipitation rate. You can think inches per hour. And overlaid on top of it is this characteristic curve of the declining rate of potential infiltration. So we all know that potential infiltration starts high and then it decreases because the soil pores are filling, the suction head is decreasing, and now it's only gravity that's drawing the water downward into the soil, and it's no longer being sucked downward by the attractive forces of the soil itself. Let me ask you before we go any further, why is it that the line is dashed when we are to the left of this location? Why does it go from being dashed to being solid? You can probably see that, when it's solid, it's in the rainfall hydrograph, but what does that mean physically? Like, what's the physical difference between to the left and to the right?
Does that have to do with, like, it infiltrating the ground?
What do you mean?
Like, initially when it starts raining, there's no runoff. It has to go into the ground first, and the ground has to become saturated.
You're right. Yeah. So you're definitely correct about that. There hasn't yet been any excess yet. So why not? Well, remember that this is the precipitation amount. So the precipitation amount was less than the infiltration rate. And so you're only going to see excess when the precipitation rate exceeds the infiltration rate. So to the left of this curve, all of the water has been absorbed. And it's only when you're to the right of this point of intersection that there's leftover water beyond what the ground is able to infiltrate. So that's why this dashed line, it was when it was the potential infiltration. It wasn't yet an actual infiltration rate because it could have absorbed more water than it did. But there was only this much rainfall. Now they've labeled the IA, F, and PE. That's just them labeling different parts of the rainfall hydrograph. And so what they're saying is that the NRCS method assumes that the first thing that happens is a certain amount of the rain satisfies initial abstractions. Initial abstractions are surface wetting interception, and like ponding. So first those are satisfied, and then after that is accomplished, then the water begins to infiltrate into the soil. So F sub A is the water that's retained. So it's water that's reaching the ground, infiltrating downward to the soil, and then what's above the infiltration is the precipitation excess. So P sub E, rainfall or precipitation excess, is what you can think of as runoff. The units sometimes can be confusing because sometimes we'll talk about runoff with units of inches, and sometimes we'll talk about runoff with units of volume per time. And so here in the NRCS method, remember that all of these amounts, P sub E, F sub A, I sub A, they're all going to be units of either depth in absolute terms or depth per time if it's a precipitation rate. But then we would use a unit hydrograph to translate the depth of rainfall into a flow rate. Okay, so this formula that's shown says the precipitation, so the entirety of this rainfall hydrograph is the precipitation excess, the initial abstraction, and the retention. So the NRCS model says that when it rains, the water goes one of three places. And that's that. It's like a mass balance approach. The water comes down from the sky, and it's either wetting the surfaces, which is the initial abstraction, penetrating into the soil, which is the F sub A, or running off, which is the P sub E. So that's the NRCS method. Now, and I think maybe we've touched on that idea before, but what's new is the way that they account for what they're introducing as storage. It's the maximum capacity of water that could be stored by the soil. And they've developed this ratio where they say that the ratio of the infiltrated quantity of water to this concept that they're introducing as storage is the same as the runoff to the overall precipitation minus the initial abstraction. So effectively what that is it's at a certain time the actual amount of water that's stored to the potential amount of water that can be stored. So we'll look at some applications of this. It's a little bit of a fuzzy concept at first, I think, but I think that you'll understand more about what the NRCS method is saying on a time step by time step basis once we give this a try on a few examples. Now, the way that they account for initial abstraction is they just say it's 20% of the overall storage. So that's not very satisfying, but that's just that's what they assume. So S, how do we know what S is? We'll look at a table of how S is calculated in a moment, but just to return to this idea that being a mass balance, the water that's coming in to a certain control volume is coming in as rainfall. Then there's a certain amount of water that's retained in the soil, wetting the surface, wetting the vegetation, and then what's left over is the runoff. So the NRCS method is a mass balance approach. Now, S, storage. Initial abstraction, remember, according to the NRCS method, is 20% of the storage. And they say that there's something called a curve number. CN stands for curve number. And we'll look at a table of curve number values, and you'll see how the curve numbers themselves address these factors: soil properties, land cover, ground slope, stream characteristics. It's through the curve numbers that those factors are accounted for. So you use the curve number to calculate storage, and storage has units of length. And so all of these terms here, F sub A, S, P sub E, P, I sub A, they all have units of length. And so does S when calculated with curve numbers. And then the NRCS equation, like if someone said write the NRCS equation, it's this. It's the relationship between storage, precipitation, and precipitation excess. And so if you have the initial abstractions satisfied, then this equation applies. But if the initial abstractions aren't satisfied, then there's no rainfall excess. And so if P, the precipitation depth, is greater than 0.2 S, remember 0.2 S is the initial abstraction. So this is just saying if you have a big enough storm that you wet the surface, you satisfy all of the interception effects, and now there's going to be more precipitation beyond the initial abstraction, then this is how you can calculate the precipitation excess. But if you don't have the initial abstraction satisfied, then there won't be any runoff. So this is the NRCS equation, and this is just simply how you calculate S. S has units of inches. So sometimes we use SI units, and you'd have to convert from inches of S into SI units. But these curve number tables are based on traditional units of inches for depth. So this is jumping ahead a couple of slides. If you've got them printed out, I think this may be material that's a few slides ahead, but I thought maybe it fit better in today's lecture. So the first thing that you have to do to know what curve number to use for a watershed is to consider the soil properties. And there's such a wide continuum of soil types that what they do to assign these soil classifications is their minimum infiltration rate when the soil is full, fully saturated, it's voids, and you just have gravity drainage. So think about a loose sandy soil, maybe would have a gravity-driven drainage of 0.3 to 0.45 inches per hour. A soil that is clay would have a minimum infiltration rate of 0 to 0.05 inches per hour. And then here in between would be sandy loams, decaying organics, and so in the middle a little bit. And there is a fourth class of soil, heavy plastic clays, soils with high salinity, soils that swell when they're wet. So in West Virginia, most of our soils are group C. And you can occasionally in a watershed see maybe 5 or 10% would be B or A. Normally that's at the bottom of a channel. Like if you think about, if you've hiked through watersheds and so on, when you're crossing a creek, you'll see sand and silt and loose soils because that's what has been scoured and moved over the surface, and it makes its way to the bottom of the stream. But most of the hillsides will be rocky, clay, and sometimes even plastic clays. And so we generally have group C and D soils even. And so the first thing is just to think about the type of soil that you've got. And so then once you know the type of soil you've got, you look at how the land is being used, for what purpose, what sorts of things are growing there, what kind of industry there might be. And so you'll look at, this is a table that describes developed urban areas. So it's not a natural land anymore. It's been disturbed from its original, but the case of lawns will have relatively low curve numbers. But if you look at paved areas like roads or roofs, driveways, this is saying that you'd use a relatively high curve number. And there's no curve number that's higher than 98. So it's not a linear thing. You can't think of this as a percentage. This isn't the same as a curve number. So it would be a mistake to think of it as like 98% impervious. But the higher the curve number, the less water is going to be retained by the soil and more runoff there will be. And so for an impervious surface, it doesn't matter if you've got well-drained sandy soil or poorly drained clay soils. You have the same curve number. But for lawns, it does matter. So if you've got grass on top of sand, then there's going to be relatively less runoff and more storage. But then if you have that same grass, but it's on top of clay soil, then there would be less storage. So you can see that tables like this will look at urban areas that are developed, commercial districts, residential areas with, typical quarter-acre lots, and how that maybe varies as a function of the soil type. And then there are even curve number tables that looks at things like different types of mixed woods, forests, meadows. So in a couple of weeks, we're going to start using a program that's called WMS. And I'll give you a table of land use characteristics that is specific to West Virginia. And so it has all of the soil type and land use designations that you'll see in a data set that's provided by the USDA. And we'll use that. It's like a map that tells you at every point in the state how the land is being used and what kind of soil they've got. So these are curve numbers. And once you know the curve number of the soil, you substitute it into this formula. So the CN is the curve number. And then that would tell you the potential maximum storage in the watershed in inches with that formula. All right, so let's get a little bit of practice applying the NRCS method. All of the formulas that we need are here on the screen. And let's calculate two different situations. The first is if there's 7/10 of an inch of rain in this watershed, which has a curve number of 70. And remember, what we have to do is determine whether the initial abstractions, excuse me, where the initial extractions have been satisfied. So this 0.2 times the storage, if the precipitation is less than that, then you don't use the NRCS equation. But if the precipitation amount is greater than 0.2 times storage, then that is when you do use the NRCS equation to predict what will be the runoff depth. So we want to know how much rainfall excess will there be for a 7/10 of an inch storm and a 3.5 inch storm. Okay, so I'll pause for a second. You begin by calculating S. Already given you the curve number, so let's take a look. You can see already on the whiteboard I mentioned that if there's 0.7 inches of rainfall, that we're not going to see any excess because it doesn't satisfy the initial abstractions. So a watershed that the soil and land use combined give us a curve number of 70. The potential for storage is 4.286 inches. Now you might think, well, why would there be any runoff if the storage potential is 4.286 inches? Because, in the second example, we only have 3.5 inches. But remember, it's also about timing. That it just may be that the rainfall occurs more quickly than the soil can absorb at any given time. But in this first depth of 0.7 inches, then there will be no rainfall excess. In the second condition of 3.5 inches, then the precipitation excess amount will be just over an inch. Did anybody else get that same value of just approximately 1 inch of rainfall excess? And so if we look at where it's going, we can use this equation to calculate how much infiltration we expect to see. And so the infiltration quantity is the storage multiplied by the ratio of precipitation excess and the difference between precipitation and initial abstraction. So 1.63 inches is going to go into the soil. So the rest of it, if we calculate the initial abstraction as 20% of the storage depth, about 0.8 of an inch goes there. So it all adds up to the 3.5 inches of rain that we know occurs. So there is a mass balance, in equals out here. And so this tells us the distribution of where it's all going. Any questions about the NRCS method? So what you should be able to explain is, it's not just enough to put numbers into equations, but you should also be able to explain what factors does the NRCS method account for, and what's the underlying rationale or methodology. The mass balance idea that you've got a certain amount of precipitation described by the rainfall hydrograph, and what the NRCS method does is it breaks up the quantity of water that will satisfy initial abstractions, the quantity of water that can be accommodated by the soil, and then the leftover amount is the runoff quantity. So on the homework that I've just posted, assignment 7, there is a question on problem number 3. And what you can do on that problem is find out how much precipitation there's been up to a certain time, and use this method to predict how much infiltration there will be up to a certain time. So here we've just rearranged this equation, and we're expressing it in terms of up to a certain point. So S doesn't vary based on time. It's just a maximum storage quantity. Initial abstraction also doesn't vary based on time. But what does vary is how much precipitation there's been up to a certain point. So if we were to take this rainfall hydrograph as an example, then we can find out how much precipitation there's been up to a certain point in the storm by putting into this formula. And that's what that question asks you to predict. Remember, F is the infiltration amount. So if you, let me just pull up that problem so we can look at it. So assignment 7, problem 3. So you're told that during the first hour there's 1.5 inches of rain, during the second hour 2.5, and during the third hour 1 inch. And so what we want to know is for each hour, how much precipitation has there been to that point, and it's cumulative. The abstractions that have been satisfied up to that point. So initial abstraction is an amount you can calculate based on the storage quantity, but how much has been satisfied of that initial abstraction? And then how much of the retention has occurred up to that point? So basically you're doing a mass balance on an hour-by-hour basis. But the hint I wanted to give you is that the precipitation is cumulative. So during the first hour you have 1.5 inches of precipitation, but then at the end of the second hour, you have a total of 4 inches of precipitation because it was the 1.5 in the first hour and the 2.5 in the second. And so this formula that we've just looked at, P, is the cumulative precipitation amount that's occurred up to a certain point in time.